our group 2 elements, right? So group 2 elements are here. So the elements such as beryllium, magnesium, calcium, strontium, barium, and of course radium, ending with radium. Let's end with radium, right? So radium, right, would be the last one there. These are all our group 2 elements. And we know that our group 2 elements are part of the S block, right? Right? There are S block elements. So let's start off here. The atomic numbers from beryllium going to radium, right? So we have beryllium being 4, magnesium is 12, calcium is 20, strontium is 38, barium is 56, and radium is 88. And let's look at these properties. Now, while we look at this table and scan this table to look at the trends, because I want you to look and then for yourself you can figure out the trends because we can read with understanding, right? Let's look at what the syllabus wants us to understand. We must explain the variations in the properties of the elements, right, in terms of the structure and bonding. So we must specifically speak about the atomic radii and the ionic radii, right? As well as the ionization energies. We must be able to describe the reactions of these elements with oxygen, water, and dilute acids, explain the variation of the solubility of their sulfates, explain the variation of in the thermal decomposition of carbonates and nitrates, and we must also discuss the use of some of these compounds such as magnesium, or the compounds of magnesium and calcium, right? We have to look at those uses, right? So we know that magnesium and calcium magnesium oxide and calcium oxide and as well as their hydroxides and carbonates can be used for many important or many daily practices. Let's say that many daily practices. All right. So that's what we're supposed to be looking at. So here we already have our metallic radius, right, which is our atomic radius technically, right? And then we have our ionic radius here, and our density of these compounds, or well, these elements, the melting points, and the first ionization energies. And I hope we've all read them and looked at the trends that we can see. All right. So the trends in atomic radius, we know that atomic radius always decreases going down a group and increases going down a group and decreases going across the period. So down every group, atomic radius must decrease. Well, increase rather. I'm mixing up my increase, decrease, but yeah, it's increasing, right? It gets larger. Atoms get larger going down the group, right? Ionic radius now, we know that ions, if the atoms get larger, then the ions get larger. That must make sense, right? That must make sense there, guys. All right. So hold on. I hear somebody joining the meeting, but I'm not in the meeting on my phone. Give me a moment. Let me just let them in real quick. But yeah, so we have that there, right? Our density now, we know that as we go down the group, density increases. We know what density is, yes? Everybody should know what density is. So the density increases going down the group. Right, the melting point as well. We know that metallic, go ahead. The melting point slash boiling point, we have that there, and then the first ionization energy is actually decreasing going down the group. Let's have a look at this, right? Atomic and metallic radius. Now, the metallic and ionic radii, right, both increase down the group, right? So we know why. Successive energy levels, right? We have screening effects. We have the fact that the orbital shielding is different. All of that. Do we have to explain this? The first thing we explained this before in group 4, right? We don't have to go back through that. We don't have to. So just know that atomic radii increase going down. All right, lovely. Density now. The density depends on the mass of the atoms and the way they are packed in the lattice, right? So at higher levels of chemistry, then we're gonna look at packing, right? FCC and PCC packing and stuff like that, right? But at this level, we'll just talk about the fact that okay, they're packed differently, all right? So from calcium to barium, there's an increase in density. Then from beryllium and magnesium have higher densities than calcium because they are packed more efficiently in the lattice with less wasted space, right? So that's what's happening. I won't get into what packing is. It is not necessary at this level. All right. So that's just information there. Ionization energy now. The ionization energy is the energy needed for the complete removal of a mole of electrons from the outermost shell of a mole of atoms to produce a mole of cations, right? So this, on descending the group, the number of shells increase. Therefore, the outer shells are more shielded from the nucleus and less closely held, right, and easier to remove. Therefore, the ionization energy of the atoms decrease down the group, the first ionization energy, right? So we have that there. We know that already. Metallic point melting points now, sorry, rather about that. Metallic point, melting points, right? The stronger the metallic bond, the harder it is to separate the cations. So what does this mean? This means that the melting point and hardness are higher if the metallic bond is stronger, the metallic bonding is stronger. So on descending the group, the size of the cations increase and the charge of the cations remain constant, right? So the charge density thus decreases and the attraction between the cations and the delocalized electrons actually decrease. Thus, there's less energy required to melt the structure. The melting point and hardness therefore decreases. Right? So that's what we have there. Hoping that we're following. Right? So we know that so for example, the melting point of radium is actually 700 degrees Celsius and the melting point of barium is actually 730 degrees Celsius. So note how the melting point is decreasing because the charge density decreases. Right? So when the charge density decreases, the attraction to delocalized electrons actually decrease, and that means that the metallic structure itself is weaker, and that also translates the metallic to the melting point and the hardness decreasing, right? So that's what's happening. So we have that there. We're now asked to look at the chemical reactions. Let's look at the subtlety of these things, right? What's happening now? Go ahead.
Sir, can you explain why the melting point of magnesium is less than the melting point of calcium, please?
All right. So the melting point of magnesium. Okay, hold on. There's a difference there. Hold on. Did I not catch that? Aha. Okay. I forgot about that. Right. So the melting point of magnesium, right, it's actually smaller. Does anybody know how to explain that? What is the reason?
Sorry,
Go ahead.
sorry, is it because magnesium has a different lattice structure?
Is it because magnesium has a different lattice structure? All right. So that is one approach. Okay. Does it though? It is true. It is true. All right. So it is a part of the packing, right? That we were talking about the density of the elements, right? So beryllium and magnesium has higher densities, right, than that of calcium, right? So there's a difference here, right? So the strength of the bonds are important with the melting points here, right? So although we know that magnesium, right, has a stronger metallic bond than calcium, right? Well, let's look at this now. The magnesium atoms are actually loosely packed compared to calcium, right? So magnesium atoms are loosely packed compared to calcium, right? So what does that mean? Else, there's less energy needed to break the metallic bond in magnesium, and therefore we would know that the lower melting point must be attributed to it, right? So this would have a lower melting point than calcium. Notice that it's lower than that of calcium, right? Why is that? Right? Magnesium atoms are actually loosely packed compared to that of calcium. So since their packing structure, their lattice structure is different, as the person rightly stated, right? It's going to be easier to isolate magnesium atoms rather than calcium atoms. And if it's easier to isolate them, that means that the melting point is actually going to be lower, right, than compared to the energy required to isolate the calcium atom, right? So the melting point of magnesium should be lower than that of calcium because of the structure of the lattice, all right? Magnesium is less dense than calcium, all right? Okay, hopefully that covered it. Was it Amelia who asked? Is that fine, Amelia?
Yes, sir.
All right, lovely. If anything
Yes,
else,
sir.
yeah, if anything else becomes foggy, just ask. Okay. So,
Okay.
okay, so we know that if we have a negative E naught, we will lose electrons more readily. We know that, right? So we're looking at the well, we know what E naughts are. We know. We've done module 2 long time. No, but all that is about, right? So we're here saying that beryllium is actually not beryllium, barium is actually the element that is most reactive. So the reactivity of group 2 elements increase as we go down. B, reactivity. All right. So the reactivity actually increases as we go down. So barium is more reactive than strontium, which is more reactive than calcium, which is more reactive than magnesium. Sorry, yeah, the magnesium. All right. So let's look at this now. So since the reactivity increase is going down, we can see some trends here with the reaction of oxygen, water, and acid, right? So with oxygen now, first of all, group 2 elements, what is the name of group 2? The traditional name for group 2. These are what?
Alkaline earth metals.
Metals.
The alkaline earth metals, lovely Jeremy, right? So the alkaline earth metals, right? So therefore, right, when we're what therefore they're going to show regular reactions with oxygen, right? But different with water. So let's just have a look at this now. We can see that magnesium itself, right, will actually burn with a brilliant bright flame, right? White flame actually. So it's a white flame, keep in that mind, right? With oxygen to form magnesium oxide, right? All burn readily in oxygen, right? So the reactions are highly exothermic and reactivity increases down the group. So all the group 2 elements tarnish in the air as a layer of oxide is formed on the surface of the metal, right? So if we are to, let me see if this makes sense. Give me one moment. Let me look at something. All right. So if we are to really look at that, we're going to have a quote. Okay, what I wanted to really look at is whether or not you guys required a picture. But if you guys Google, right, any picture of any of these any like calcium or magnesium, right, you should actually see, right, you should actually see the fact that when you cut it, right, it's much shinier when we cut it, right, and then after a while oxide layer will cover it, right, and that is one of the things that we can tell its reactivity from, right. So it tarnishes in air. The oxides are basic in character, so upon reacting these oxides with water they will form hydroxides, right. So calcium oxide will actually form lime water, right, because calcium hydroxide is lime. That's why it's called lime, right? So lime as in limestone, in calcite, and those type of minerals we find them. So lime in water gives us lime water. That's basically it. So calcium oxide in water gives us calcium hydroxide. Lovely, right? The reactions of the metals with water, directly with water, not its oxide, or itself in water, will actually give us hydroxides because they're alkaline earth metals. We know that they will form basic hydroxides in water. All right. Calcium, strontium, and barium all. Well, let's look at this. Magnesium actually reacts very slowly in cold water, so it reacts very slowly when the water is cold, but reacts rapidly in steam to form magnesium oxide and hydrogen gas. So that's what's happening here. So in the water here, right, at a low temperature, and the water here at a high temperature. How do we know the difference in temperature? This here is gaseous and this here is liquid. right? So it reacts in steam to form magnesium oxide and hydrogen gas, right? But in water, it reacts slowly. Regular cold water reacts slowly to form magnesium hydroxide, right? So it reacts slowly with water, producing that hydroxide there. So this reaction soon stops as the magnesium hydroxide is insoluble, and then there's a barrier between the magnesium, preventing further reaction. So after it drops into the water, it's going to form the hydroxide coating and then remain there, right? With calcium, strontium, and barium, they all react in water in increasing vigor, right? To produce metal hydroxides and hydrogen gas, right? So the hydroxides are not very soluble, so we know the solubility of the group 2 hydroxides decreases as we go down the group. The solubility of the group 2 hydroxides increases, right? If they are not really soluble, it increases, my bad, right? So it actually increases going down the group. So here, the solubility of the group 2 hydroxides increases going down the group, right? So when we create the metal hydroxide, the hydroxides are not very soluble themselves, right? But barium hydroxide would be more stable more soluble rather, than strontium hydroxide and etc. going up the group, right? So the solubility of the hydroxide increases going down the group. Thus, less precipitates are seen, right, down the group because more hydroxides dissolve in water. So a white precipitate of calcium hydroxide is formed when calcium reacts with water, and it is dissolved, right, to form a weakly alkaline solution. All right, so that's what we have there. So the resulting solutions are more alkaline going down the group, of course. So basicity also increases going down the group. So basicity increase going down the group, solubility of the hydroxides increase going down the group, reactivity increases going down the group. So a lot of them tend to increase going down the group. All right. Reactions with acids now, right? So a metal and an acid will give you hydrogen gas, right? So let's look at this. So all the group 2 metals will produce hydrogen gas and a salt, right? So let's look at this. If it's reacting magnesium with the hydrochloric acid, it's going to give you magnesium chloride and hydrogen, right? And we know that reactivity increases down the group. Therefore, calcium will be more rigorous than that of something like magnesium. Okay, so calcium reacts more vigorously with acids, while barium reacts violently, right? So we're looking at stuff like that. With sulfuric acid reacts with barium insoluble barium sulfate forms, right? Which coats the metal and then prevents it from reacting, right? So we have stuff like that happening. So generally, what this is saying is that generally, when we react with all our acids with hydrogen chloride or hydrochloric acid, it will form a chloride and hydrogen gas, right? And when we're gonna react most of our metals with sulfuric acid, will create a sulfate and hydrogen gas. But something like a beryllium, right? Beryllium sulfates are generally more soluble because solubility of sulfates actually decrease going down the group. Okay, so if we're looking at this now, the solubility for the group 2 compounds, let me see if this is relevant information. Break the lattice ions, release energy and hydrate. This is the explanation for the solubility, right? Specifically. So this is in terms of the lattice energy and hydration energy. So we know solubility. Low solubility results when the lattice energy exceeds the hydration energy. I hope you guys remember that. I'm not sure if we did it in solubility product, right? But when the lattice energy is larger than that of the hydration energy, then you're going to see that the substance is actually insoluble, right? So solubility product is actually somewhat proportional to the lattice energy, right? So this is just information explaining, and I'm gonna send you guys the document, right? Or I can pause and look at it, right? So this is just an explanation of it specifically, but you won't necessarily use a lot of this information, right? When answering the group 2 questions, right? But we will make mention to the lattice enthalpy and the enthalpy of hydration, right? We're gonna make mention to it. So the lattice enthalpy is greater than when the lattice enthalpy exceeds the enthalpy of hydration, the substance is insoluble, right? And when the enthalpy of hydration exceeds the lattice energy, the substance is soluble. Hopefully, we can remember that from solubility product, all right? The sulfates now, right? The lattice energy decreases going down the group.
Sir, sir, sorry. Excuse me. Can
Okay.
you repeat that, please?
Okay.
Can you repeat
So
that, please?
okay, so let's repeat that. So the lattice energy, if the lattice energy is larger than the enthalpy of hydration of the substance, right? What we're gonna have is the substance being less soluble. That is because what is lattice energy? Can somebody define that? What is lattice energy there? What's that?
The energy required to break the lattice into ions.
Okay, so the energy required to break the lattice into its constituent ions. Lovely, right? But what is the enthalpy of hydration?
The energy the ion releases when it's already in its ion.
All right. So the energy releases when the ions are fully dissolved, right? So what we're saying, if the energy, right, if the lattice energy is greater than that of the enthalpy of hydration, then when the thing is dissolved, is going to be put into water, right, that energy is going to be way greater than the energy required to actually dissolve the substance. Therefore, it will be insoluble. But what happens when we have an enthalpy of hydration being actually greater than that of the lattice energy? We're going to actually have the substance dissolving, right? So it's going to be soluble. So that's what we're talking about. So if the lattice energy, right, so as we stated here, the lattice energy specifically, attraction of those, where is it? Where is the statement? If the lattice energy exceeds the hydration energy, then the substance is actually more insoluble. But if the hydration energy exceeds the lattice energy, then we're going to have the substance being solid. All right? And we can make reference to it here. If the lattice energy decreases down the group, then we can note the solubility of the sulfates, right? Because as you can see here, the solubility of the sulfates actually decrease going down the group. So barium sulfate is more insoluble than strontium sulfate, which is more insoluble than calcium sulfate, which is more insoluble than magnesium sulfate. All right, hopefully that makes sense. So we decrease that's enthalpy, right? Going down the group. So the decrease is actually fairly small, right? So there's not really a large difference in the solubility, but the solubility changes, right? So the size of the cation increases increases. However, this increase in the size is negligible compared to the large size of an anion, right? So what we're saying is that the lattice enthalpy is fairly small because it is determined more by the size of the large sulfate ion more so than the cation, right? Remember, the size of the ions can be used to determine, right, our lattice energy. Remember, we spoke about that and we did that in the first marathon, right? We spoke about that. The size and distance of ions determine the lattice energy. But in this case, we have a low lattice energy, right? Because more so because of the large size of the sulfate ion, more so than the cation that we deal with, right? So bullet points now. The enthalpy change of hydration also increases in the same order. It becomes more positive. Because if we know this now, if we have a decrease in lattice energy, we are going to have an increase in hydration energy or the enthalpy of hydration, right? So this decrease, so we're gonna have that, right? It becomes more positive, right? However, this decrease is relatively larger because it is determined more by the size of the cation than the anion. So what we're looking at, hydration is more likely determined by the size of the cation, right? And lattice energy is more likely determined by the size of the anion and not the cation, right? So as the size of the cation increases going down the group, the charge density decreases, and this decreases the force of attraction between the ions and the and with the polar water molecules, right? So the charge density is decreasing as we go down the group, right? Because the larger the ion is, the larger the atom is, right? The larger the ion rather, right? The larger the ion, the smaller the charge density in this case, right? As we go down the group, charge density decreases, and charge density can define how much electrostatic attraction we have, right, between the anion and the cation. So if our charge density decreases, our force of attraction will decrease, right? So the enthalpy of solution gets more endothermic going down the group, and we know what the enthalpy of solution is. The enthalpy of solution speaks to what? Go ahead.
So the energy change, sir.
The energy change in which occurs when 1 mole of a solute dissolves completely
All right.
to form,
Go ahead.
hmm? so, to form an infinitely dilute solution
All
under
right.
standard conditions.
Okay, so when it completely dissolves in the solution, right? So we're just keeping it at that concept here just for this. All right. So when it dissolves, right? So the complete energy change when it dissolves, right? If that now becomes more endothermic, right? Specifically, endothermic are positive values, right? We're actually going to act, it decreases solubility, right? So if the energy required to dissolve the solution becomes so great, right? There's going to be a point in which we cannot overcome it, right? Therefore, it will remain insoluble, right? So it's same thing with solubility constants, right? When we speak about KSP, we have to increase the temperature of the solution in order to dissolve. So we need to increase the temperature so we can match the enthalpy of solution, so we can allow the enthalpy of hydration to surpass the lattice energy so the thing can dissolve, right? So what this is really speaking about is the main reason why things dissolve, because if we put like sodium chloride in water, we just take it for granted that it's dissolved. But what's happening with the sodium chloride is that the enthalpy of hydration surpasses the lattice energy of sodium chloride, and there's enough kinetic energy, right, within the solution for the enthalpy of solution to be reached. Therefore, the salt dissolves, right? So it's all of that that takes place, right? So to remember that chemistry is a study of these things, study of why these things happen, right? So the solubility of the group 2 sulfates, right, actually decreases going down the group, and conversely, it increases going up the group. Simple. And that's the solubility we have there, right? We know that solubility speaks to the mole per 100 grams of water, right? The mole of substance increase in the solution per 100 grams of water, right? So that's what solubility, right, will speak to in this case. All right. So we know it decreases going down the group. For the solubility of our carbonates now, soluble carbonates, solubility of the carbonates actually decrease going down the group, right? It's generally the same thing here. So the decrease in solubility is similar to the sulfate. So we have to speak about the lattice energy exceeding the hydration energy, and the enthalpy of solution becomes more positive going down the group. Therefore, carbonates decrease in solubility going down the group. So which will be more soluble, our strontium carbonate or magnesium carbonate? Which is more soluble? Strontium carbonate or
Sure,
magnesium carbonate?
magnesium.
You're saying there's strontium carbonate?
Magnesium.
It would be magnesium, right? Because magnesium is above strontium in the series, right? In the group. Alright? For hydroxides now, right, solubility of hydroxides increase going down the group, and we looked at the hydroxide ion thing, right? The hydroxide ion is actually very small, right? Compared to sulfates and carbonates. Therefore, the lattice energy actually decreases significantly as we go down the group, because the large positive ion, the cation, will actually be the thing that we are looking at right here. So the size of the cation will actually be, will actually have more significance, right? Will actually have more significance compared to the hydroxide ion. So if you look at it, the larger the anion, the more likely the thing is to be insoluble, right? Because the small cation and a large anion, all right, the small cation can actually polarize the orbitals existing around the large anions, right? Hopefully that's expressed here. Okay, it's expressed in thermal stability, right? I think it's expressed in thermal stability a bit, right? But it's similar to what was happening up there. Hopefully, let me see if there's a diagram. So the diagram here will attempt to explain. So I'm gonna explain polarizability down there. Alright, it's something similar to what was happening in our attractions, force of attractions, right? So thermal stability of the group 2 compounds now. We did state it in qualitative analysis earlier that carbonics tend to be thermally well not they tend not to be thermally stable, right? But they have different thermal stabilities. So let's look at this now, right? Thermal stability basically speaks to the fact, right, how easily, right, are these compounds decomposed at certain temperatures, right? So is it that if we change the temperature to 300 degrees Celsius, is it going to just decompose into carbon dioxide, oxygen, and its parts like that? Or is it going to remain stable at high temperatures, right? So nitrates now, the nitrates of group 2 undergo thermal decomposition to give the metal oxide and nitrogen dioxide gas. So we know if we heat these group 2 metal oxides, this is what we get. This is literally a reaction that we can see coming out from qualitative analysis, right? It is used in the determination of our nitrates, right? So going down the group, the nitrates become more stable, so higher temperatures are required to decompose them. So the thermal stability of nitrates increases going down the group, right? So as we go down the group, the size of the cations, right, themselves decreases, right? Therefore, there's a polarizing effect that occurs, right? So the smaller, highly charged cations are more polarizing and tend to attract electrons clouds, right, of the nitrate ion enough to weaken the structure and break the bonds, right? So looking at that, let me actually change this. Let me look at that for a second. Give me one moment. Let me look over this, all right? Polarizing effect, smaller height, all right, that should be fine. So if we're looking at the size of the cation, right, the cation can actually what we call polarize the molecule, right? So the smaller it is, right, the higher the charge density, so it tends to increase the poles, right, the strength of the poles on the molecule itself. All right, just giving us 1 second here. Just pausing for a second. All right. So we don't want to run across everything. So I believe there is a this seems so much like an interesting Alright, so we have the increase in size going atomic size going down the group, so there's a decrease in cationic size. Right, so therefore we're looking at the polarizing effects specifically. Right, so the more a substance is polarized, the easier it is, right, to actually break the bond. And that's because the degree of covalency actually decreases, right? So what does covalency speak to? We know that covalent bonds, right, are will arise from situations in which compounds, right, or elements actually share electrons, right? If we continue to increase the polarization on the molecule and one becomes increasingly positive and the other becomes increasingly negative, the electrons are going to actually be held, right, much closer to themselves, right? So what's going to happen here, right, if we have two strongly positive, well, strongly charged, right, strongly charged molecules or particles, right, what's going to happen is that electron affinity and ionization energy will take hold, right? So the one that should be losing, right, will achieve its electron affinity, and the one that should be positive will achieve its ionization energy, and then they will actually switch electrons. So electrons will swap, a redox reaction will occur, right, and we're going to have the creation of ions, right? So we know that ionic substances are substances that are held together by electrostatic forces. So if we have a covalent molecule and we're increasing the charge, right? Increasing positive charge or increasing negative charge, right? It's going to increase so much so it acts like two completely charged particles, and now electrostatic forces will have to ensue. So the more we polarize the molecules, the more they behave like ionic compounds, right? So they lose what we call the covalency. So it decreases their competency for covalent bonds and ionic substances specifically, right? Yeah, so it actually increases their bonds specifically, right? So it actually decreases the covalent bonds, right? The strength of covalency, the covalent bonds, and the bonds what they're making now would actually be ionic in nature, right? So it strengthens their bonds specifically, right? So I hope you guys get that part though. It sounds kind of murky, but what we're saying is that the compounds get so much charge, right? So polarized, one becomes so positive and the other becomes so negative, it behaves like it's ionic, right? So its covalency will decrease, therefore, majority of the energy keeping the substances together will be electrostatic, right? And because the distance between them are going to be so small, right? It's going to. I'm hoping if you guys do physics, it's going to be similar to Coulomb's law. The two charged particles are going to be so close together. The energy required to move them apart will be way more, right? Would be greater than if it was covalent. So it's going to have strong ionic bond characteristics, right? Rather than its regular covalent bond characteristics, right? And that makes the compounds more stable because we know that ionic compounds are more stable thermally than covalent compounds. So the more ionic you are, the more polarized you are as a covalent compound, the stronger your bond. And that's what's happening with the nitrates, right? So the nitrate stability, right, actually increases, right, as we are actually going down the group, because that charge density is now increasing, right? And you're able to polarize the molecule better. So your molecule loses its covalency and has more electrostatic interactions, allowing the bond to be way more stronger and not easily thermally decomposed. Hopefully that wraps it up there, right? Same thing for our carbonates. The carbonates of group 2 undergo thermal decomposition to give us carbon dioxide gas and our oxide, right? So let's look at this. Group 2 cations have the same charge, 2 plus, but why do they change? Why does thermal decomposition change or thermal stability change as we go down the group? As we go down the group, the size of the metal cation increases, right? The smaller the cation, the better it is at distorting the electron cloud, right, of the larger carbonate. The smaller ions are better polarizers of larger ions, so you have the polarizing effect, right? So group 2 carbonates with small ions have a greater degree of covalency, right, in the ionic bonding. So the greater the degree of covalency, the less energy required to break the bond. So hopefully that makes sense. So what's happening here now? We have our group 2 metal, right? Here specifically, right? And we have the localized electrons existing in our carbonate because we know our carbonate actually has a resonance structure. So we have the localized electrons here. So the oxygen atom, right, is well on its way to become an oxide atom, right? Why? Because there's going to be some electrostatic interaction between these two. So two differently charged molecules, right? So the smaller the molecule, the atom, the not the atom, the cation is, the more polarizing it is, right? And it allows for this bond to lose its covalency and become more ionic. All right. So that's what's happening there. Now, for the use of group 2 elements, now we know that magnesium is used commonly in group 2, right? Usually it's for the creation of lightweight alloys, right? So, magnesium, right? So magnesium is an example of an alloy between magnesium and aluminum, right? So we can use magnesium as an alloy, right? It is used in the manufacture of cars and aircrafts, right? And we also have magnesium oxides, right, which are used in the refinery lining of furnaces, right, at high melting points and low because of its high melting point and low reactivity, right? So we have that there. So we know the melting point and reactivity of our substances, so we should be able to relate them, right? It is used in medication to relieve heartburn. So usually you see magnesium in some amount of tablets, right? So magnesium sulfate as well is used as a powerful laxative, right? So I have some examples there. And you guys should know generally magnesium sulfate, like Epsom salt, magnesium sulfate, heptahydrate. That is what Epsom salt is, right? Magnesium sulfate, heptahydrate. It's a covalent, it's a complex compound, right? Calcium, strontium, and barium have less uses because of their high reactivity, right? Calcium carbonate, though, right, actually is used in the construction industry, so building materials. So marble, or using marble, right, or an ingredient in some other type of building material, so cement, etc., right? It is used widely in the medical industry, so dietary calcium supplements are also there, and it can act as an antacid, right? Calcium carbonate itself, right, and calcium oxide and calcium hydroxide are also used in the agricultural industry to counteract soil acidity, right? So when you have runoff and those type of things due to high rainfall, right, we can actually replenish the alkaline substituents in the soil, right? And we know what's happening there, right? Because if we have runoff of minerals which are alkaline, right, the microorganisms in the soil will continue to create acids, right, and increase the soil acidity. So what we need to do is counteract that by adding these compounds, these alkaline earth metals, back into the earth, right? So these are also used in water treatment. So it reduces acidity as in flocculant. Flocculant is something that we use in the treatment of water, right? In the industry specifically, they are also used as scrubbers to disulfurize waste gases and to neutralize acidic effluents, right? So in the creation of sulfuric acid via the contact process, etc., we use these in what we call in the tubes, right? That release the air, right? That release gases from industry. So usually when we have those huge towers in industrial complexes releasing all that what we call smoke into the air, we can use these compounds to actually trap the acidic substances, right? So we prevent acid rain from being an issue, right? Because acid rain is sulfuric acid. When the sulfates go up in the air, react with water to create sulfuric acid. So if we can use these substances as what we call scrubbers, we can desulfurize the gases, so we have a smaller chance of acid rain, right? Calcium oxide is also what we call quicklime and reacts exothermically in water to create calcium hydroxide, right? And it is sufficient to heat or ignite combustible materials in some instances, right? So we have that there. So we can use it to we can also use calcium hydroxide to actually extinguish fires when we react it with water as well, right? We also have barium sulfate, right? It can be eaten as a part of a barium meal, right? So it can be consumed because it's really unreactive in sulfate, because we know that barium sulfate is really insoluble, right? It can be eaten, right? And it's good at absorbing X-rays, right? Therefore, what are we looking at, right? If magnesium sulfate is actually consumed, right, it can outline parts in the guts, right? Um, by using X-rays, right? So what it's gonna do when it goes through the gut, you can actually use X-rays to see the path of the barium, right, sulfate, right? So although barium ions are very toxic, this technique is harmless because barium sulfate is completely insoluble, right? So we have that there. And we know that our elements here, group 2 elements, are using fireworks as well because of the flame test. Barium gives a bright green flame, right? Strontium is a crimson flame, right? These different types of colors are given out in fireworks. So when you go to fireworks shows and see fireworks exploding, when you see the red, it is most likely some strontium or lithium, right? When you see green, it's most likely it's gonna be less likely copper, because why copper? It's gonna most likely be barium, right? So those different brilliant colors that you see in firework displays, our metals are being used, right, under high temperatures. All right. So that is basically it for the review of group 2 metals. Are there any questions?